In this lecture, we are going to see the topic undecidable problems about Turing machine, and PCP is nothing but post correspondence problem in unit 5. We are familiar with what is undecidable problem and what is Turing machine. So in this lecture, we see one theorem that is for undecidable problems about Turing machine. So that undecidable problem on Turing machine is called as halting problem. So here we are going to see one theorem that is Turing machine halting problem, that is undecidable problem, right? So the input for this problem is a Turing machine and the input string. And what is the problem to be here is, does the Turing machine finish their operation, which means computing of the particular input string W in a finite number of steps? So this is the problem. If the Turing machine, because the input is Turing machine and the input string, so the question or problem here is, if the Turing machine accept the input string or does not accept this input string within a stipulated time, which means within a finite number of steps or amount of time. So the answer is either yes or no. If the Turing machine accept the input string in a particular time, then the result is yes. If the input string reject the input string within a stipulated time, then the result is no. So this is the problem of that particular Turing machine halting problem. So here we are in the process of proving the halting problem. So in the initial step, we have to assume that there exists a Turing machine to solve this particular problem, and then we have to show the contradiction also, which means the Turing machine, we have to show that the Turing machine accept the input string with either yes or no, and also contradiction means it is a reverse process, that is inverted Turing machine. So we can call this kind of Turing machine as a halting machine that produces either yes or no in a finite amount of time or in a stipulated time. So if the halting machine finishes their operation in a finite amount of time, then the output comes as either yes, otherwise the output is no. So this is halting problem on Turing machine. So this is the diagrammatical format of halting machine. So there is one machine, halting machine, that is the Turing machine. The Turing machine called as halting machine because undecidability on Turing machine is called as halting machine. So we have to pass some input string on that halting machine. So the halting machine have to accept the input string in a finite amount of time, then the result is yes. If the Turing machine does not accept the input string in a finite amount of time, then the output is no. So S means the halting machine, that is Turing machine halt on the particular input string W. No means the halting machine, HM is halting machine, does not halt their operation on the particular input string which does not belongs to the language. Now this is the concept of Turing machine halting problem we proved, right? Next one is inverted halting machine or inverted Turing machine, that is we already saw that in the second line of proof. Then we will show it is contradiction itself. Contradiction means we have to prove that the inverted halting machine, that is the contradiction concept. So it is a reverse process. A reverse process is nothing but if the Turing machine returns yes, then it goes to the loop forever. In a normal halting machine, if the Turing machine returns yes means then the Turing machine halt their operation. But it is the inverted halting machine. So here, if the Turing machine H or halting problem H returns yes, then it goes to the infinite loop or loop forever. If the halting problem returns no, then the Turing machine halt their operation. It is the reverse process of normal halting problem because it is an inverted halting machine. So the block diagram of inverted halting machine like this. There is one halting machine which get input string, and if the halting problem or halting machine returns yes, then it goes to the infinite loop. Infinite loop is nothing but the initial state is Qi, it goes to the next state Qj, and Qj again goes to Qi, Qi again goes to Qj. So it is a infinite loop, means loop forever. If the halting machine returns no, then the halting machine halt their operation. So this is the inverted halting machine. If in case this is the normal halting machine, means here if the halting machine returns yes, then it halt the operation of Turing machine. If the halting machine returns no, then it goes to the infinite loop forever. So this is the inverted halting machine, which means it is a reverse process of normal halting machine. So further we have to form another Turing machine HM2, which input itself is constructed as follows. Here also, if the Turing machine halt on input, which means if the Turing machine returns S means, then it goes to the infinite loop forever, otherwise it halt their operation, right? So here also we have to prove the theorem halting problem on undecidability by contradiction. So hence the halting problem is undecidable. So this is the theorem of halting problem undecidability or Turing machine halting problem. The problem here is if the Turing machine does finish their operation and returns yes within the finite number of time, or otherwise it does not halt their operation, which means it produces the result as no in a finite amount of time. This is the problem. So we have to solve this problem. We are using one theorem like Turing machine halting problem, and also we have to prove the theorem by the contradiction also, that is inverted Turing machine or inverted halting machine. So the next topic is post correspondence problem. It will return as PCP, post correspondence problem. So what is the use of PCP? Here we know what is undecidable problem, which means we can't give any solution for that particular undecidable problems. So undecidable problems about Turing machines is nothing but the Turing machine involved in the process of reduced that particular undecidable problem into another undecidable problem. So here the new concept is reduction. We have to reduce one undecidable problem into another undecidable problem. That is the concept of PCP. So the goal of this problem is to prove that problem about the strings to be undecidable. So we can take one undecidable problem as an example, and then we are using some algorithm on that particular undecidable problem. So that particular undecidable problem have to be reduced to another undecidable problem. That concept is known as PCP. So here in that diagram you can see that MPCP. MPCP is nothing but modified post correspondence problem. So it is a reverse process. We have to reduce or convert one undecidable problem into another undecidable problem, that is PCP. Again we have to reduce that undecidable problem into another undecidable problem, that is MPCP. That is the modification of PCP. So LU is universal language. So the universal language can be converted or reduced into another problem by using some algorithm A, that is MPCP. So again we have to use another algorithm B to convert the reduced problem into another reduced problem, that is MPCP into PCP. So the initial LU is considered as PCP. So PCP is converted into MPCP using some algorithm A, and MPCP is converted into PCP by using some algorithm B. So in this diagram we can clearly understand that we can convert easily PCP into MPCP and also MPCP into PCP. So this is the definition about the PCP. So an instance of post correspondence problem consists of two lists of that strings over sigma input alphabet. There are two lists, one is capital A and the second list is capital B. And the list A can be written as W1, W2 and WK. These are each and every individual input string. W1 is one input string, W2 is another input string, and up to is go on. WK is another input string. So the next list is capital B, is a combination of x1, x2, xk. Here also x1 is one input string, x2 is another input string, and xk is last input string. So here we are we are having two lists A and B which hold the input strings. So the instance is nothing but is a solution of the PCP has some solution if there are any sequence of integers I1, I2 up to Im with the condition of m greater than or equal to 1, such that we have to equalize the above two list strings. A is equal to B. So A has the value of 1, 2 can be replaced by I1. So Wi1, Wi2, Wi3 and up to Wim is equal to B list, B having x1, x2, xk. So here also we can substitute I1, I2 So xi1, xi2 and up to xim. So this is the solution of instance of PCP. You can clearly understand if we can see one problem for PCP and MPCP. So in the examination they have to ask the question like this. They are giving some input alphabet, let sigma is equal to 0, 1 and they are giving two integers because PCP having two list value A and B. So each and every list having individual input string only. So the question is find the instance of PCP. So in the last line you can see that this is the solution of instance of PCP. So to find out the solution we have to equalize the two list strings, right? So here also in the table they are giving. So in the table having two lists, one is list A, list B. List A means wi, list B means xi, and also they are giving the integer values I, 1, 2, 3. I is equal to 1, I is equal to 2, I is equal to 3. So w1 value is 1, w2 value is 1, 0, 111, w3 value is 1, 0, x1 value is 111, x2 value is 1, 0, x3 value is 0. So these are the given values to find the solution of PCP. So we have to find this integer value I1, I2 and up to Im. This is the solution of this particular instance of PCP. So consider here the solution is given in the first step itself. The solution is 2113. So 2113 in the sense these are the integer value. 2113 is the integer value. So by concatenating these strings in the series of, we can take W2, W1, W1, W3 is equal to the same order. We can't change the order for the second list. For what order we have to take or we have to apply for the first list, we have to follow the same order of the integer to the another list also. So is equal to x2, x1, x13. So the order value is 2113 and right hand side order is 2113. We can't change the order. So after the second step you can apply the value for W2 in that given table. So W2 value is 10111 and W1 value is 1. W1 value is 1. W3 value is 10. So the result of W2, W1, W1, W3 is 10610. So we are proceeding with the right hand side. So x2 value is 10, x1 value is 111, x1 value is 111, x3 value is 0. So after substituting these values you can check whether the both list values should be equal. You can check whether the left hand side and right hand side value of equal for the order or combination 2113. So this is the solution of this instance of PCP. So this is the formula or this is the definition to find the solution for PCP. And you can better understand about this. We can repeat the integer value at any times, because you can see that 2113 here we are using the integer value 1 at 2 times, 2113, and you can use 2, 3 integer values at multiple times, but whatever you have to apply for both lists, it should be equal on both sides, right? And also we have to follow the same order in both sides. For example, in the left hand side if you are using 2113, in the right hand side you can't use x2, x1, x3, x1. You can't change the order. In both sides the order should be equal, 2113. This is PCP, right? So this is the second problem on PCP. Here the same question, they are giving a sigma input alphabet and two lists A and B and find the instance of PCP. The same value, list A, list B given, Wi, Xi given. So W1, W2, W3, X1, X2, X3 we know. So in this point you can apply any type of integer, any order of integer value to equalize the two lists A and B, Wi and Xi. But this problem doesn't have any solution. You can apply any order of integer, but you can't get any solution or any order or any combination for this PCP problem. So here the result is the instance of PCP has no solution. You can check after this lecture. You can take that integer value 1, 2, 3 and you can apply any order. W1, W2, W3, W2, W3, W1 or W1, W1, W3. You can check whether if any of that particular order or combination both list having same equal value, right? But this problem has no solution for this PCP. So what is MPCP? Modified PCP. We know what is PCP. So what is modified PCP? It is a little bit different from PCP because we can easily convert from PCP into MPCP and also MPCP to PCP. There is a little bit difference because you can see that the modified PCP also having two lists A and B. A and B are having the string value W1, W2, Wk and X1, X2, Xk. So it has also having this solution like I1, I2 and up to IR, and here also we have to equalize the two list value A and B, right? So the main difference between MPCP and PCP is that the solution for MPCP is required to be stored with the first string on each list, which means you can see that in the equalization value W1, WI1, WI2, WIR, and also the right hand side X1, XI1. But you can see that in PCP WI1 it will start with WI1 and the right hand side it will start with XI1. But for MPCP it will start with W1. After W1 only WI1 should be present. Similarly, after X1 only Xi1 should be present. So the meaning of this MPCP is we have to start the equalization with the first integer value, right? You can understand when we see the problem. So this is the same problem like PCP. They are given input alphabet sigma is equal to 0, 1 and two list A and B. A is Wi and B is Xi, and they are given W1, W2, W3 value, X1, X2 and X3 value. So we have to find the instance of MPCP. So same concept, we have to equalize both lists Wi and Xi. We can put any order of that particular integer value, but the main difference is we have to start only with W1 and X1. So you can see that here they can equalize the value but start with W1. Here the result is 1, 3, 2, right, which means it will start with only 1, right? But you can see that in PCP the problem combination have to start with the instance is 2, which means we can given the solution for any order of integer. Here the initial integer value is 1, but the solution having the first result is 2. But for MPCP the solution will start with the first value. Here the first integer value is I is equal to 1. So here the solution will start with 1. After 1 you can change the order or combination of any integer value, 1, 2, 3 or 1, 2, 2, 1, 1, 3. You can change the order of that integer, but for MPCP the initial order, the solution will start with the initial integer value of 1 only. So this is the main difference between PCP and MPCP. So there is one algorithm or theorem for MPCP to PCP. Already I said that we can convert PCP to MPCP and MPCP to PCP. So there is one theorem. The theorem is nothing but MPCP reduces to PCP. So in this point we should know about PCP and MPCP. We know what is PCP and what is MPCP. So the theorem is MPCP reduced to PCP. So we will start with the proof by the definition of MPCP and PCP. So both PCP problem having the solution as I1, I2 and Im, right? So we know that for MPCP the equalization of two list value is, we have to write the definition of MPCP, right? W1, Wi1, Wi2 and up to Wim is equal to x1, xi1, xi2 up to xim. So here the W can be replaced by Y and X can be replaced by Z. So the equalization statement can be written as Y1, Yi1, Yi2, Yim is equal to Z1, Zi1, Zi2 and up to Zim. The only difference is that the first string would be missing for PCP. So we can write it as the closure value. So for that we have to include in the first statement is closure Y1, Yi1, Yi2 is equal to Z1, Zi1. The last statement we have to include that closure value star. By using the construction rule, we can replace that star y1 into y0 and star Zim into z0. So it can be replaced by the second statement. And also we have to, in this statement we can replace star y1 and by y0 and Zim by z0. And also we have to append the particular index value k plus 1 for the conversion of MPCP into PCP. So at the end of the each statement they are writing the value or appending the value k plus 1. So for this the solution of PCP is 0, I1, I2 and I2 k plus 1. Right, this is the solution of PCP. But for MPCP the solution is I1, I2 and up to IM. So if we remove the star value, closure value and the final dollar value from the above statement, we get the string is W1, WI1, WI2 and WIM. And also if we remove dollar and star symbol in the above statements, we get the result is X1, XI1 and up to XIM. So for PCP we have to equalize the value, the same statement in the previous slide, Y0, YI1, YI2 up to YK plus 1 is equal to Z0 up to ZK plus 1, which follows that W1 X1, because we have to replace W by Y and X by Z0. It is a reverse process. You can see that, right? Actually in the first step W1 is equal to X1, after W1 is replaced by Y1. Similarly here Y0 after replaced by W1. So this is a solution of PCP implies that the solution of MPCP instance. Thus that is the meaning of reduction of one problem into another problem, which confirms that if PCP were decidable and MPCP also decidable. So in this lecture we saw about halting problem and PCP and what is MPCP. So PCP is we have to reduce one decidable problem or undecidable problem into another undecidable problem. So our aim is to reduce one undecidable problem into another problem that is decidable, because we are going to reduce one undecidable problem into another. So our aim is to the problem have to be reduced. So reduced means the problem should be decidable. So the undecidable problem can be converted into another decidable problem by using some algorithm, that is PCP. And also we have to, if the reducible problem is again got as undecidable by PCP, then also we apply another algorithm B on that particular undecidable problem, that is MPCP. So PCP and MPCP goal is to reduce one problem into another problem.